I want you to take a second and just picture a 5-year-old. You know the type I'm talking about.
Oh, I do.
They are chaotic, they are loud, they're enthusiastic about absolutely everything. They probably can't tie their own shoelaces yet.
Not a chance.
They certainly can't read a novel. Their handwriting, I mean, it usually looks like a seismograph reading during an earthquake.
That is a very evocative and honestly a pretty accurate description of the kindergarten experience.
Right. So here is the question that anchors our entire deep dive today. Can that child, who is still struggling to figure out which shoe goes on which foot, learn computer programming?
I mean, that sounds like a trick question.
A little bit.
Yeah.
But I don't mean just playing a game on an iPad where they smash candy. I mean actual logical algorithmic thinking.
Right. Because we usually associate coding with, complex syntax, abstract logic, late nights staring at lines of text on a screen. It feels like a skill that requires a certain level of cognitive maturity that a 5-year-old just doesn't have.
Exactly. But we have this fascinating piece of research on the desk today that just challenges that assumption entirely.
We do.
We are doing a deep dive into a study titled An Educational Robotics Experiment conducted with 5-year-old pupils to learn coding, decoding design.
And it is a very thorough, very dense piece of work. This comes to us from researchers in the north of France, specifically the Nord-Pas-de-Calais region.
And the scale here is important.
Well, it's huge. They didn't just look at, 5 kids in a lab. They took 230 pupils across 28 different classes. These are year 1 students, so roughly our kindergarten equivalent.
And just to set the stakes here, these aren't prodigies. These are typical kids. They are non-readers.
Right. Their handwriting is still developing. They're just learning to count.
Which is actually critical for what we're talking about. The researchers weren't trying to teach them, I don't know, Java or Python.
No, not at all. They were using the Explore the World section of the French curriculum, specifically the parts about spatial awareness, to sort of sneak in computer science concepts.
So the mission of this deep dive is pretty clear. We want to find out how you teach algorithms to a toddler. But more importantly, we want to settle a debate. What works best?
The big question.
Is it a physical robot? Is it a tablet screen? Or is it using their own bodies? Because the results from this study, well, they disrupt a lot of our modern assumptions about digital natives.
They are definitely surprising, but before we get to the results, we have to look at how they set this up, because the methodology is really quite clever.
Okay.
They created a placebo group.
I love that they called it a placebo group. It sounds so clinical for 5-year-olds.
Right.
Like they gave them a sugar pill instead of a robot.
It is essential for the science, though. This group, labeled P in the data, did the pre-test and the post-test, but in between. They got nothing. No coding lessons, no robots, no serious games.
They were the control. But why is that necessary?
Yeah.
Obviously, if you teach a kid something, they learn it. Do we really need a control group to prove that teaching works?
You absolutely do with this age group. You have to remember, 5-year-olds are development machines. Their brains are growing so fast that sometimes they just get smarter because they got 3 months older.
I see.
So the researchers needed to prove that any improvement was because of the specific lessons, not just, natural biological maturation.
So what did the stats say?
The statistical analysis proved that the active groups, the kids who actually played the coding games, progressed significantly better than the placebo group. It confirms it. 5-year-olds can actually be taught sequential programming.
So it's not just random luck or them getting older. The lessons worked.
The lessons worked.
Okay, so we've established they can learn. The big question is how. The researchers used these serious games with 3 different methods or modalities, as the paper calls them. Let's unpack those.
Yeah, the tools here matter a lot. So the first one is the body modality, or B. This is where the child essentially is the robot.
So they're physically moving around.
Exactly. There's a checkerboard taked out on the floor, and the child has to move box by box while other kids give them instructions. It's what educators call embodied learning, right?
Right. It grounds the abstract concept of an algorithm in physical space.
It does. If I take a step forward, that is one line of code. If I turn my body right, that's another line. It uses the body's own sense of position to teach the logic.
Okay, so that's body. Then you have the robot modality, or R. This used a toy called a blue bot. What is that?
It's perfect for this age. It is a little floor robot, looks a bit like a bug.
Yeah.
You press buttons on its back to program it forward, backward, turn left, turn right.
So it's very tactile.
Very tactile. Click, 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 and then you press go, and it executes the whole sequence on a tabletop grid.
And finally, the tablet modality, or T. which is what I think we all picture.
A virtual version of the same game on an iPad screen, dragging and dropping commands. But here's where it gets really interesting. They didn't just test these individually.
They mixed them up.
They mixed them up. They had groups that did body, then robot, or robot, then tablet. They were looking for the perfect cocktail of learning.
That's smart. Now, unfortunately, the data for the body plus tablet group got lost.
Which is a classic research hazard.
So the deep dive really focuses on comparing body, robot, tablet, and those powerful combinations like robot plus tablet.
Exactly.
Okay, before we get to the winners and losers, I want to clarify what learning actually looks like here, because you said they can't read or write well, so they aren't typing code.
No.
What are they actually being tested on?
It wasn't a written exam in the traditional sense. It was broken down into 3 specific cognitive tasks. And understanding the difference between these tasks is key to understanding why some kids failed.
Okay.
The first task was decoding.
Decoding. Break that down for me.
The child looks at a line of arrow symbols on a paper, up, up, right, up, and they have to draw the path the robot would take on a grid. They are translating symbols into a trajectory.
So they have to simulate the robot's movement in their head.
Right. Input to output. Then you have coding.
Which is the reverse.
The reverse. The child sees a drawn path on a grid, and they have to write out the arrow symbols to match it.
That sounds harder. You have to break down a continuous line, a movement into discrete steps.
It is significantly harder. It requires a higher level of abstraction. And then the third task, the mission, was programming design.
This sounds like the final boss battle.
It basically is. The child gets a grid with a starting point, 2 flowers, and a bird. And the instruction is, invent a path that reaches the flowers but avoids the bird. And then they have to code it.
So they aren't just following instructions, they are solving a problem. They have to plan.
And they were even scored on optimization. If they took the short path, say 7 instructions, they got a better score than if they took the long way around with 9 instructions.
Assessing optimization skills in kindergartners.
Yeah.
That is wild. I know adult programmers who struggle with optimization.
It is very impressive.
Okay, let's get to the results. Because I think everyone listening probably has an assumption here. We tend to think kids are digital natives.
Right.
We hand them an iPad at a restaurant to keep them quiet, and they can navigate YouTube before they can speak in full sentences. So logic would suggest the tablet group would crush this.
And that is exactly where the data throws us a massive curveball. The expert analysis of the tablet alone group, the kids who only use the screen, was remarkably poor.
Really? Define poor.
In the decoding activity, the tablet group had the highest number of negative grades. 25% of them fell into the regression category.
Regression, you mean they got worse?
Yes. A significant portion of the tablet group performed worse on the post-test than they did on the pre-test.
That is shocking. You send your kid to school to learn coding on an iPad, and they come back knowing less than when they started. What do you think happened?
It suggests that for this age group, the screen might be too abstract. When you are 5, physical interaction matters. If you are just dragging things on a screen, you aren't getting that haptic feedback.
You aren't feeling the space.
You're not. You might not be internalizing the logic of the sequence in the same way you do when you press a physical button or move your own body. So the screen in isolation might act as a barrier to understanding, not a bridge.
It seems to detach the cause from the effect.
That's a good way to put it.
So if the tablet was the loser, who was the winner? Was it the body group? The kids moving on the floor?
The body group was the reference point. It was safe, it had low regression, so it didn't confuse them, but it didn't produce the highest highs.
Yeah.
It's a good starting point, but it has a ceiling.
Okay, so who won?
The clear dominance belonged to the robot plus tablet RT group.
The combo.
The combo. This group had the highest percentage of what the researchers called honorable grades. We are talking 44% receiving top marks in decoding and 54% in the design task.
That is a huge jump compared to the other groups.
It is, and this leads us to what the paper calls the double modality hypothesis. The researchers noticed that the groups who used 2 methods, specifically robot and tablet, consistently outperformed the monomodality groups.
I have to play devil's advocate here. Is it just because they spent more time? If you do robot and tablet, aren't you just doing twice as much coding?
That is the big question.
Is this just practice makes perfect?
Time is certainly a factor. The researchers admit that the bimodality group spent twice as much time on serious games, but the expert analysis in the paper suggests it's not just time.
No?
If it were just time, you would expect linear improvement across the board. But we see specific patterns. The robot plus tablet group shows signs of what educators call scaffolding.
Scaffolding. Unpack that for me.
Imagine building a house. You need a structure to hold it up while you build the walls. The physical robot acts as that scaffold. It builds a concrete mental model. I press button, thing moves.
I see.
Once that model is solid in the child's brain, moving to the tablet allows them to practice manipulating that model in a more abstract way. The robot builds the foundation, and the tablet lets them test the boundaries.
And jumping straight to the screen, like the tablet-only group did, is like trying to put the roof on before you've built the walls.
That's it. That's why they regressed. They didn't have the foundational mental model to make sense of the abstract pixels.
Well, that makes perfect sense. But speaking of things that don't make sense, there was a weird anomaly in this data that I want to drill into.
Yes, the paradox.
The paradox. We talked about the 3 tasks: decoding, coding, and design. Logic would dictate that coding, just looking at a line and writing the arrows, is simpler than design, right?
You would absolutely think so. Design is cognitively much heavier.
But the kids actually did better on the complex design tasks than the simple coding task.
This is what I call the paradox of coding versus design. And honestly, it is one of the most fascinating parts of this study. You look at the charts, and for the coding activity, there is a huge spike in low and regression grades, especially for the bimodality groups. But for design, which is harder, they soar.
So what is going on? Are these kids geniuses who get bored by simple tasks but thrive on complex challenges?
Maybe a little bit, but the answer is likely much more physical. The researchers did a qualitative analysis. They actually looked at the test papers the kids handed in.
The seismograph handwriting?
The seismograph handwriting, figure 15 in the source material, is just heartbreakingly illuminating. It shows the test papers. Some of these children struggle physically to draw the arrows.
Oh, I can just imagine. You ask a 5-year-old to draw a right turn arrow and it ends up looking like a squashed bug.
Or a plate of spaghetti, exactly. The coding task required them to look at a grid and translate it into a specific sequence of drawn symbols. That is a fine motor skill challenge. A child might know exactly what the algorithm is in their head, but their hand can't execute the symbol on the paper.
So the test wasn't just measuring their coding ability, it was measuring their ability to draw.
Precisely. And if the teacher grading the test can't tell if that scribble is a left turn or a forward arrow, the child gets marked wrong. That explains the high regression in the coding task. It wasn't a failure of logic, it was a failure of motor skills.
But wait, the design task also required them to write down the code, didn't it? Why did they do better there if they still had to draw the arrows?
This brings us to meaning-making and constructivism. In the design task, there was a narrative.
The bird and the flowers.
Yes. Avoid the bird, get the flowers. That gives the task meaning. The child isn't just abstractly drawing arrows, they are telling a story about a robot's journey.
It anchors the abstract concept in a concrete goal.
Correct. The researchers believe this context helps the child construct meaning. When the child is thinking, I need to get away from the bird, the direction becomes intuitive. Away means right. It bridges the gap between the thought and the symbol.
Whereas in the pure coding task, there is no bird. There's just a line.
It's purely abstract, and that is where they stumbled.
That is such a powerful lesson for education in general. Context matters. If you just give kids a worksheet of arrows, they fail. If you give them a mission to save a robot from a bird, they succeed, even if the underlying math is the same.
It is the difference between rote memorization and applied knowledge, and for a 5-year-old, that narrative element is the glue that holds the cognitive process together. It lowers the cognitive load of the motor task because the intent is so clear.
So let's look at the final scorecard here, the body group.
The body group was the reference point. Safe, it had low regression so it didn't confuse the kids, but it didn't produce the highest highs. It's a solid foundation.
And the robot group, on its own.
Solid performance, much better than the tablet alone. It confirms that physical toys are better than screens for this age, in isolation.
And the winner, robot plus tablet.
High risk, high reward. It produced the smartest kids, the highest percentage of honorable grades, but it also had that weird regression in the coding task, which we think is linked to the motor skill issue. But overall, it showed that the double modality effect is real.
So the takeaway for a parent or a teacher listening to this is, don't just pick one method. Don't just buy the app.
And don't just buy the toy. The magic happens in the combination. And perhaps more importantly, realize that coding for a kindergartner is just as much about moving their body and telling a story as it is about logic.
And maybe cut them some slack if their arrows look like spaghetti.
Please, if they can get the robot to the flyer, they understand the algorithm. Don't let the handwriting test fail the future programmer.
It is really encouraging, though, isn't it?
Hmm.
This study proves we can teach sequential thinking before kids can even read.
It opens up a huge door. We often think of screen time as the enemy or the savior. This shows it's neither. The screen is a tool, but it's a tool that works best when it's anchored in the physical world.
There was one other concept in the source material that I found really poetic: the mirror effect.
Ah, yes. This comes from the idea that children identify with the robot. They project themselves into the toy. It's not just a piece of plastic.
It's an avatar.
Right. When they program the robot to move, they are essentially programming themselves. If I were the robot, I would turn right. That projection is what makes the learning stick. It connects back to the body modality.
So they start by being the robot on the floor, and then they transfer that identity to the Bluebot toy.
Exactly. And maybe that is why the tablet alone failed. You can't project yourself into a flat piece of glass in the same way you can into a little robot that bumps into things.
There is a lack of empathy with a touchscreen.
The robot exists in your space. It shares your physical reality. That connection is powerful.
So what does this all mean for the listener? I mean, assume the person listening to this is not 5 years old.
Well, hopefully not. But the principle of double modality applies to all of us. Think about how you learn a new skill. Do you just read the manual? Or do you just try to do it physically? Usually you fail if you only do one.
I do this all the time. If I have to fix the sink, I watch the YouTube video, that's the screen, and then I try to physically fix the sink.
Exactly. And if you only watched the video, you wouldn't get the feel of the wrench. You wouldn't know how tight to turn it. But if you just grabbed the wrench without the video, you'd probably flood the kitchen.
Probably.
We are all still learning like 5-year-olds. We need to combine the abstract information with the physical application. The study shows that this isn't just a preference, it's a statistical advantage.
That is a great perspective. We are all just big kindergartners trying to figure out the grid.
And hopefully avoiding the birds along the way.
I want to leave you with a thought. We talked about the mirror effect, projecting yourself into the robot. Next time you are struggling to solve a problem, maybe step away from the screen. Walk it out. Literally walk the grid yourself. You might find that your body knows the answer before your brain does.
Sometimes the best computer is the one you are walking around in.
Thanks for diving in with us. We will catch you on the next one.